Concurrent algorithms is an EPFL Master-level course given by Professor Rachid Guerraoui. But what is a concurrent algorithm?
A concurrent algorithm is an algorithm that executes on several processors inside the machine, and these processors access the shared memory.
How is it different from a class on distributed algorithms?
In a classical centralized algorithm, you have a set of instructions, and typically they go one after the other. In a concurrent algorithm, you typically divide your algorithm into pieces in order for these pieces to execute in parallel. A priori, things go smoothly when these parts are completely parallel, but in reality, they are not. There are very, very few programs for which you can really have a full parallel execution. So usually these algorithms, these pieces depend on each other, and sometimes they have to wait for each other, sometimes they have to access the same information, and that's where problems come, and many bugs come from the misuse of concurrency and parallelism.
How is this different from classical centralized algorithms?
So this is the second class I teach. In a distributed algorithm, the processors or the machines communicate by message passing, and they fail somehow independently. In a concurrent algorithm, here we assume that the processors access the same shared memory. They don't usually exchange messages. They are in the same machine. And we don't assume that they fail independently in the sense that, for example, if an attacker controls a machine, he or she controls all the processors. It's not going to control part of them. So we don't have this notion of malicious failures that we have in distributed algorithm. You have more problems of access to same shared data and interleaving and problem like that.
What are the applications of concurrent algorithms?
We use them everywhere. It's important to understand that maybe 20 years ago or even 10 years ago, people would write an algorithm, put it on a processor, on a machine, and then wait a little bit, change the processor, and then the algorithm will go faster. But things have changed because now we cannot simply change, modify, switch the processor and hope that it goes faster, because today the speed does not come from upgrading the processor, really, it comes from adding more processors to your algorithm. So you cannot really take a nap and hope that the algorithm goes faster by changing the processor. You have to work hard, and working hard means exploiting more processors that are available, and therefore people have to write these algorithms, and therefore they have to understand these topics. But today, probably all practical algorithms run on different processors.
How is the class different from a class on operating systems?
In a class on operating system, you understand the basic software and hardware tools. You understand what a lock is, what a semaphore is, but understanding how to use them in order to build effective, efficient, and correct algorithm is a different matter. And this is what we understand in this class. What is a correct concurrent algorithm? When can we say that the algorithm is correct? What is really a bug? How do we prove that the algorithm is correct, and so forth?
What about the differences with the class on architectures?
So again, in architecture, you really understand why things go fast. You understand really the mechanics of parallelism, the mechanism of shared memory, etc. You don't study correctness in the theoretical sense. You don't study complexity of concurrent algorithm. You don't get the patterns of writing this algorithm. So this is what we study in this class, how to write correct and fast concurrent algorithms.
What are the concepts that are taught in concurrent algorithms classes?
So this class goes in a very, very incremental manner. We assume a very simple architecture of a machine where you have different processors that access a very simple shared memory. And then we ask, given this shared memory in hardware, what kind of shared object or abstractions can we build on top of it? For example, can we build a shared counter? Can we build a shared compare and swap if it's not given in hardware? Can we build a queue? Can we build a producer-consumer, and so forth? So we try to study what abstractions can we build and what abstraction we cannot build, such that when somebody has to write an application, we somehow understand the basic abstractions that are abstractions of shared concurrent objects.
Is the teaching theoretical or practical?
It has both aspects. So there is a practical project where students will learn how to use a shared memory multiprocessor architecture to write an effective algorithm. But there is also a theory part where students really have to understand what is correct, what is complexity, what is possible, what is impossible, and how to write proofs in this context, and so forth.
Are there prerequisites to the class?
The prerequisites here are, as we pointed out, some basics of operating systems, some basics of architectures are useful, but in terms of theory, first order logic and concepts of algorithms are useful, but there is no advanced mathematics needed. Some topology might be needed in 1 or 2 classes, but it's not really a big prerequisite.
Will the class be useful to students after they graduate?
They use it all over the place because, as I pointed out earlier, pretty much every algorithm today executes, it is distributed, but also within every machine it executes on several processors, and therefore you need to master concurrency, because if you don't master it, either you have an algorithm that doesn't run fast or it runs fast but it's bogus. So having both is a challenge, and in most cases today you have to master concurrency.